she was in medical school, and they had like cappuccinos that were like, it was like probably like a machine that you just go put a quarter in and get a little cup of cappuccino. And before she knew it, she had like 10 of them one day. And
Oh, that's a lot.
she was like describing her symptoms to one of her colleagues, and they're like, well, sounds like caffeine poisoning.
Crazy elevated heart rate.
Yeah, elevated heart rate, and just kind of, I think something happens with your breathing, like, well, you kind of know, you've seen people. Just kind of jittery, and, man, I wish I could remember all the symptoms, but it also happened to a student of mine who, he used to do the 8-hour energies, or was it 4-hour?
5-hour.
5-hour, yeah. He had too many of those for too long a time, and started feeling not quite right. Fortunately, he stopped before it hurt him, but
How many Celsius do you have today?
I don't know.
Let's not talk about my caffeine.
I will, I'll begin with a repair. Heavenly Father, we thank you for this day. Again, I thank you for this class, and just ask you to guide our steps today. Help us to glorify you. We do, Lord. In your name I pray, Lord Jesus. Amen. All right, so if I can find my notes, that would be good. Oh man, I didn't bring the book today. That was dumb. Oh, wait a minute. Seriously? Oh, well, that's annoying. That is very annoying.
You should have brought mine.
I did not. I am not thinking clearly today. I'll tell you that right now. I have a scan of it on the computer. It's just I have to, load it up. And I don't know this stuff by memory. Let's see if I can find it. So we're talking about quotient spaces, right, and the quotient topology. And so we've gone through a number of examples, of course. And, oops, went into the wrong. I wonder if I saved it.
Because this is good timing.
Rats.
Because in algebra, we are currently learning about quotient groups.
Oh, yeah?
You just told us what they were, yes?
Ah.
So,
Well, I guess if you have a quotient, if you have a group, right? Well, I guess the question is, the notion of quotient group the same as the notion of, well, they are related. I wonder what more we could.
what I was thinking about
Mhm.
was how we're talking about a quotient space looking like R mod tilde or something. And
Mm-hmm.
and the quotient map, the natural map at least we were talking about, maps everything to its quotient or its equivalence class. But with quotient group, we have like G mod H.
Yeah.
And isn't that the group of the cosets? So, and every element in the group is in a coset.
So yeah, I mean, with the quotient space, we're
Which is an equivalence.
talking about a set of sets, but the sets are formed by either use left or right, probably left group code, like GH. Is that the typical form of your cosets in abstract?
Yeah, like AH.
Fine, AH. So like the set of AH, where A ranges over the group, is a set of cosets, and then you have to suppose that the group is normal in order to give the set of cosets themselves a group structure, which we call the factor group. You guys do that already?
We actually call it the coset group, the identity. But something.
I hope I'm not spoiling your abstract algebra.
I didn't say factor yet.
I think we just ended on defining factor group.
Really?
It was the last.
So you talked about the subgroups being normal?
Yeah, so like the
Okay.
left and right cosets are the same.
The triangle thing.
Well, this is suboptimal, but it'll have to
Oh,
do.
you did say factor group.
Yeah.
Okay.
All right, so how did we define the quotient topology last time?
Let x, let me read it. Or are you going to write it up? Or?
Yeah, I'll write it up here a second. Let me. All right, man. I'm sorry. I'm still annoyed. I didn't bring my notes. So.
Let x be a topological space.
Mm-hmm.
Let y be any set.
Y any set.
And q maps x to y is surjective.
Q mapping x to y surjective. Okay.
Define the topology on y by declaring u subset y open if and only if the inverse image under q of u is open in x.
So here's a way of saying that. So the topology on y, it's subsets of y for which the inverse image under q is in the topology on x. All right. So if that's, in this case, the we have more language too, right? What do we say about, what do we call q something, right?
Quotient map.
The quotient, yeah, the quotient map. Yeah. Oh, come on, you stupid. Not you guys. I'm talking to my computer. It's the stupid one. All right. So he says, but he's also got stuff about the partition, right? Most common application of the quotient topology is following construction. You have an equivalence class relation on the topological space X, and you have, typically you look at Q, a mapping from X to X mod some equivalence relation, right? And then, and Q is in particular the equivalence class defined by X, right? And then X paired with this quotient topology induced by Q is called the quotient space. So this is also called the identification space of X by the given equivalence relation. All right. Then we looked at some examples. There's something else I wrote on the board last time. I'm trying to remember what it was.
Homeomorphism?
Well, yeah, we talked about homeomorphism.
And q is continuous.
What was that thing I said about Q continuous and quotient?
If q is a quotient map, then q is continuous.
If
And
Q,
it's like pretty simple.
if Q is quotient map, then Q is continuous. Something else I said. I wrote it like here-ish.
I know what you mean. Are you talking about if x and y are topological spaces, a map q mapping x to y is called a quotient map? If q is surjective and y is quotient topology induced by q?
That was it. So say that again. If
If x and y are topological spaces, a map q mapping x to y is called a quotient map. If q is surjective and y has quotient quotient topology induced by Q.
If, what did I just say? If Q is surjective,
Yeah. And Y has quotient topology induced by Q.
induced by Q. All right. Cool. That was it. All right, so let's see. Let's try to come up with an example. Example one. Let's see here. So,
Should I remind you of the examples we did last time?
yeah, I'm just trying to. Well, no. I'm trying to think of a new example.
Well, I'm sure reminding the other ones that you don't say.
Oh, I know which ones I did. I'm all the way to the projective space example. That much I remember, but this I kind of pulled out of the middle of the paragraph. So, yeah. So, how about you guys? Do you guys have any ideas for a potential quotient map? Like, what's a couple of topological spaces which are interesting, perhaps? How about, oh, I don't know. We can let X, yeah, well, here's what we'll do. We'll let X be, this is going to be a bizarre example, but here we go. X is Rn by n with the metric topology. Induced from the Frobenius inner product. So if you don't know what that is, it's this. If we have AB, it's the trace of AB transpose, which is just a fancy way of talking about, like that is literally just the formula for A11, B11, plus plus ANN, BNN. So it's the pairwise product of components from A and B summed over all possible components. In other words, it's the inner product of A and B thought of as n squared vectors, dot product. So there you go. That's the Frobenius inner product. So we're going to give it the metric topology, right? And then I'm going to let y equal to the reals with the discrete topology. Do you guys know what the discrete topology is?
Is that every set you don't know? Or is that
So that, yeah,
every set?
that means the topology of y is the power set
Yeah.
of R. All right. So yes, every subset is open. All right. You guys with me so far? What's a good continuous map from, Q to, from X to Y? How about this? Let's let Q of A equal to, oh, I don't know, determinant of A. Or if you like, we could do trace. Doesn't matter. See, that would make, so Q of, Q is a mapping from Rn by n to R, right?
Would that be surjective?
Yeah, can we prove this is surjective? Good question. I mean, second example, let's do this as Q1. Second example, trace, yeah? Let's get more out of this example. Is that surjective? Well, that's easy, right? Let R be a real number, right? Then Q2 of R times E11 is R. Where E11 is the matrix unit. Do you guys know what I'm talking about? So it's zeros everywhere except for the 1, 1 spot. The n by n matrix of mostly zeros, but just 1, 1. So that's a surjection. Surely it's continuous. I mean, is it continuous? I mean, the formula for the trace of A is literally a sum of components, and the determinant's likewise pretty clearly continuous. I mean, I can write a formula for it. Right, the formula is this. Where epsilon is the completely anti-symmetric symbol. So it's literally a product, a sum of products of components of the matrix, which means that as a formula, it's a sum of products of projections. Well, anyway, I think you can prove these are continuous. So we have a pair of continuous surjections, yeah? Agreed? So my question is, are they quotient maps? Right? Are they quotient maps?
So this might mean not knowing topology, but would there be an issue with the fact that you're bound to real numbers instead of power set of real numbers?
Oh, no. I mean, the real numbers is a topological space. I gave it the topology of the discrete topology. But are these a quotient? Is Q1 or Q2 a quotient map? Well, the answer is no. It's too late to topologize. It's too late.
Because it already doesn't have the quotient topology.
Yeah, because
It's too late to
it's too late to topologize. Yeah. See, because I already put the discrete topology on it, so it can't possibly have the the topology induced.
It's kind of an annoying example, Dr. Cook, I'm not going to lie.
Yeah, it's almost like this example was completely contrived to force this joke, and that's the only purpose of it.
Dr. Cook, you've inspired me. Really.
Now, the first time I said that joke, it naturally happened in the course of a different lecture. Like, it just happened. It was more beautiful there. But anyway. No, so, I keep repeating that Q is continuous. I'm not actually convinced that that's true. And the reason I'm relatively sure that's actually false for both of these is in the discrete. What's that?
You just lied so that you could ask us the joke.
Yes, of course. So that makes it.
I wrote it down in my notes, Dr. Cook.
You get pencil. Okay. But notice, why are these not open? This is actually helpful because in the discrete topology, singletons are open. Right? So like a set just containing one element like this is open.
And is it true that in the metric topology, singletons are never open?
Yeah. Well, let me show you. So then well, give me a second. we'll get to it. I'm not, yeah, let me not say something. So that's open, and what's the inverse image under, say, Q1 of that singleton? Well, we're looking at what? A in Rn by n, such that what? Determinant of A is equal to R. Is that an open set in Rn by n? I actually don't think it is. I don't believe it actually is. Let me see here. Let me, for instance, so we are now getting considerably off the beaten path from the handout I gave you guys, but I don't mind. I think this is fun. We got time for it. So here's an important example. Like Q1 inverse of the number 1 is equal to, well, it's n by n matrices, right? Such that the determinant of A is equal to 1. So this is actually what's called the special linear group. It's actually a group. Yeah. And because if you take two matrices with determinant 1, their product still has determinant 1. And if you invert a determinant 1 matrix, you have a determinant 1 matrix for the inverse. The identity's in there. It's a group. And I'm pretty sure it's a closed subgroup. How do I know that? Well, if I think of the usual determinant, if I think about things, so here, let's n by n. I need some notation here. So let's say this is the, with the usual topology. All right. It is in fact true that the determinant is continuous with respect to the usual topology being ascribed to both this and that. And the proof for it is actually what I just wrote down on the other board, namely that the formula for the determinant is simply a product of the components of the matrix, right? And so like, if you have a function of many variables, if you build it as a product of the component functions and a sum of those component functions, well, component functions are continuous, right? Like, for example, if you were to look at the mapping A maps to like Aij, you can prove that this is a continuous map from Rn by n to R. Some of these would make good homework problems. I'm going to try to write them up for you guys. It'll be a good sort of counterbalance to like the crazy abstract quotient space questions, right? Which are very out there. This is much more concrete and metric. So like, it's a simple matter to prove that this is a continuous map. Because if you have control of the size of the matrix, you can control how big the size of a particular element is, and that's all you need to prove continuity, essentially. So this is in fact a continuous map. And as such, the determinant is built from a bunch of those multiplied together and added together. This is just plus or minus 1. So the determinant is clearly, perhaps clearly is the wrong word, but it can be shown the determinant's a continuous map, right? And with respect to that, notice that, well, it's still, I mean, the set theory is not different. The inverse image of 1 is SLN, right? But this is closed in, the Euclidean topology for R. Why is it closed? Because R complemented by 1 is minus infinity to 1 unioned with 1 to infinity, which is the union of two open sets, which is open, right? Therefore, the singleton is a closed set with respect to the Euclidean topology. right? And in my original joke motivating example, I did give the Euclidean topology to the matrices, right? So what I can prove is closed and open with respect to the standard construction that I'm talking about here, still true when I spoil the topology by making it discrete for the reals, right? So it is still the case that this is a closed subset of Rn by n. Now that begs the question, how do I know that a closed subset is not open? Is that what you're getting at?
No.
Because I don't know
That's a
that.
good question.
I don't know that in general. There is not a dichotomy between closed and open. Like you can have a set which is both closed and open. Yeah. Mm-hmm.
Well, my question was more, doesn't continuous only say that the preimage of an open set is open? It doesn't say that open sets are mapped.
Oh no, it also, the corollary to that is that the inverse image of a closed set is closed.
Okay.
You can characterize continuity in terms of inverse images of closed sets.
Okay.
There's also a way to define topology in terms of axioms for closed sets. Kurakowski or something axioms, but it flips the script between you have to have arbitrary intersections of closed sets being closed and finite unions of closed sets being closed. So there is a problem or two in topology where taking that as the definition makes things much simpler to prove. So it's something to know about. But anyway, but let's return to that question. How do I know that being closed means it's not open? Besides just, I mean, yes, we could just go to a direct proof, you know. But there's another theorem of topology which is worth talking about, which is that if X is a connected topological space, then the only sets which are both open and closed are X and the empty set. So in a connected topological space, the only sets which are both open and closed are the whole space and the empty set. So what does it mean for a space? What would it mean for a set? So let me talk about why that is. The proof of this theorem is pretty elementary, actually. Well within our clutches. If we had a separation, right? If X was equal to the union, the union of, let's say, U union V, where U and V are open and disjoint. So some books will say that that's a disconnection. I really like that. I think that's what Lee says in his book. He calls this a disconnect. This is a disconnection because this disconnects the space into two parts, U and V, which don't meet. That if there existed this, then X would not be connected, right? But notice that in this context, like X, this is V, right? And is that, right? So recall that, oh, I'm sorry, Shane. Recall or learn for the first time that in a topological space, by definition, a set is said to be closed if its complement is open. So U is closed because its complement is V, which we're assuming is open. And V is closed because its complement is U, which we're assuming is open. So if we had a separation, if we had a disconnection for a space, then that would mean that the separating sets are themselves both open and closed. So separation, I can't spell, separation, let's fix this, separation of x equals to u union v implies u and v both open and closed. So I guess I'm not saying the separation definition quite right, because what's part of the definition of separation? It has to be. Otherwise, everything is trivially disconnected. we certainly must assume that both U and V are non-empty. Because you could always use the empty set to disconnect a set otherwise, you know? So if you think about the theorem, it starts to make sense, right? If it's connected topological space, that means that there's not a separation. Right? If you had a set which was both open and closed, then the set and its complement form a separation. Because the set and its complement are both open and closed. Right? Like if you, let's suppose U is both open and closed, right? What would that mean? That would mean X minus U, right? X. What's the intersection of x minus u with u? That's easy, it's empty, right? So you have to, and what's the union? The complement of u, union with u is everything, right? So if u was both open and closed, and it was non-empty, it would provide a separation of the space. So if the space is connected, that's impossible, right? Which means the only sets that are both open and closed are, of course, the whole space and the empty set, right? So my question for you then is, why is this relevant to my example? Right? We have the SLN is closed in the n by n matrix topology.
So we have to wonder if the n by n matrix topology is connected.
Yes, is it connected? And so here I'm going to phone a friend and have this theorem I'm not going to prove, but here's a theorem, which is that path connected implies connected, at least in the context of the matrix space. I think that's a general truth, though. The converse is not true. There are connected spaces which are not path connected. I will leave that for your future topology course, Shane. You guys have seen it, I'm sure.
I forget.
Surely Sprano went over the sine curve, topologist sine curve. How could he not? He couldn't help himself but do that.
Oh, the thing that like does this?
Yeah, that.
I actually don't know if
He didn't do that? Oh, man. You guys got to you should demand a refund.
maybe it wasn't irrelevant.
Golly, I can't. I hope you're wrong. But how can you properly confuse the students if you don't include that? Like, you have to include that, otherwise you're missing out. Anyway, so I'm claiming you can easily prove that our n by n is path connected. How would you do it? Here's a picture.
Forget the definition of that.
I'm going to make our n by n this box. All right? I'm going to take a matrix here, A. I'm going to take a matrix here, B. And I want you to tell me the formula for the path, gamma of t, that goes from A to B. And we're going to let 0 less than or equal to t less than. Okay, what is it?
Got it.
Okay. Gamma of t equals to what?
Well, is gamma of t allowed to be
Got to be a matrix.
gamma matrix? So, well,
Would it be,
it's
would it be,
I have it.
Huh.
is it the same thing for a line segment?
I need a formula.
Is it like A minus
A.
T?
Aij.
A. We don't need ij's. Keep your components out of here.
Okay, fine.
A minus
A
B minus
Times
T
1, wait, shoot.
plus
A plus
T
T,
times what?
T times.
B minus A.
B minus A, yeah.
Yeah.
There you go. That, but, okay, so now prove the complex numbers are connected. I often ask that in the first test in complex.
I'm glad you did it.
What? I'm glad I didn't, because you just put a Z here, a Z1 and a Z2 and a Z1 and put a minus, put a T, put a plus, and lo and behold, there's your path in the complex numbers that connects Z1 to Z2. So yeah, any vector space can be proved to be path connected by this argument. Every finite dimensional vector space is connected. Probably every infinite dimensional vector space is connected. I'm not certain of that, but I'd have to think about that. Maybe I'll put that in your homework. then I'll find out. So. Right?
Best way to learn.
So since it's path connected, that means it's connected, which means the only sets which are both open and closed in the n by n matrices are the whole set of matrices or the empty set. Therefore, this being a closed set, it's not an open set. In fact, this is actually a very interesting set. It's an example of a manifold. So it can be given the structure that makes it locally Rn, and it's actually an n squared minus 1 dimensional manifold. And the argument for that's really simple in some sense, because basically it's defined by one scalar equation. So Rn squared is actually, this is an n squared dimensional manifold. And so if I have an n squared dimensional backdrop and I put one condition on it, n squared minus 1 is the number of degrees of freedom afterwards, which makes this an n squared minus 1 dimensional manifold. But now I'm getting off the beaten track for this course, so let me go on. Well, thanks, guys. I appreciate you letting me play around a little bit here. Let us continue on with the examples in the handout. Yeah, I don't mind talking more about the topology of matrix groups and things like that, because these things tend to not be belabored very deeply in grad school, and I don't know, if I was a practicing topologist, I wouldn't be terribly interested probably in explaining the nuances of why the matrix Lie groups have the properties that they are, because it probably seemed kind of boring to me. Whereas for you guys, it's like bizarro world, new stuff, right? I mean, so this is the place to at least be exposed to some of these things, I think. Let me go on here though, if I can. Okay, so let's see here. The next example was real projective space, right? So this is example 3.51. And so he calls it Pn. Real projective space. And he says it's the set of one-dimensional linear subspaces, lines through the origin in Rn plus 1.
Isn't that Rn?
Here it's Pn. So, but yes. And so here's the deal. The quotient map, we're going to go from Rn plus 1, take the origin out to Rn. Right, that's going to be the quotient map. Oh, my bad, not Rn, but Pn. And so he says it's defined by sending a point x to its span. So I'll write that down. Q of x is equal to the real span. I don't really need the R, but of X, right? This is for X not equal to 0, right? Another way we could look at this would be, we could talk about, like, you know, X is equivalent to Y if and only if what? If and only if there exists K not equal to 0 such that what? Y equals to Kx. If I was to do that, then the equivalence class, right, would be the span of X, right? See, that's not quite true. Well, fine. Oof. Yeah, is that even true? By setting X to its span, we topologize Pn by giving it the quotient topology with respect to this map. This two-dimensional projective space, P2, is usually called the projective plane. It was introduced originally, of course, for the sake of perspective and drawing. Right? The point on the artist's canvas represents light traveling along one line through a fixed origin, the artist's eye. I'm not, well, sorry, it's just bugging me, like, let me use my words. Zero's in here. I don't know if it should be. Admittedly, the points in Pn are like they're whole lines, you know, with the origin deleted.
I mean, I think I remember.
Yeah?
Like, something about the map. Like, I remember a bunch of entries and then.
Oh yeah.
One there too.
Yeah, right.
Is this what we're talking about? Is that helpful or?
We might get there eventually, but at the moment, I mean, that's another way of looking at it, yeah. You're thinking about like the coordinates on projective space, which, yeah. Let's see here. So then like the next paragraph is like talking about the equivalence I'm talking about. And so he says there's an obvious identification between Pn and the set of equivalence classes. Under this identification, the map Q defined above is just the map sending a point to its equivalence class. Okay, fine. So, all right, fine. So he's saying we can write Q of X equal to the equivalence class of X, and like this is the element of Pn. Pn. Right, but maybe this is better because this is for, what's the precondition here? X and Y elements of Rn plus 1 minus 0, right? So if that's the context, then this doesn't have 0 in it as a set, right?
It's true.
So a picture, like if we look at projective one space, what's P1 look like? So if we look at the context Rn plus 1, which is R2, right? What are the equivalence classes? Well, the equivalence classes are, you know, first of all, we're not looking at the full R2, right? We're deleting, it's R2 without the origin, right? And so the equivalence class, so if X is like, X here, of course, is a pair of points, is X1 comma X2, right? But if this is my X, then the equivalence class of x is a line through the origin like that, right? And then, another one over here, and so forth, yeah? So, like that.
X equals K1.
Yeah. So, every one of those purple lines, right, which is a pair of, every pair of those antipodal pairs, right, like there's a ray and its opposite, those together are forming the point in P1, right? Like this and that are a particular point in P1. So,
It's kind of weird.
It is, yeah, I agreed. I do find it weird, but it is.
In this context, where do we talk about the projection?
The projection. Well, I mean, the quotient map, this is the quotient map, right?
Well, I don't know, it just says we're projective space, so I'm just thinking about a projection.
Oh, just like pi. You mean this kind of projection?
I think that's where like map one of the coordinates to one.
This thing? Oh, you're trying to remember the coordinate business?
Yeah.
Ah,
I'm trying to remember.
yeah. So there what was done.
Yeah.
Just a second.
I remember it.
So, for example, this one, you can look at, throw that out, and if you throw that out, right, and you look at any point that's in here, right, then you've got a point on it like x1, x2. What can you say about x1, x2? Well, you can say, the one thing you can say for sure is that as x1 not equal to 0, right? And so this point is equivalent. I can multiply by 1 over x1. I can put the k, I can do y1, y2 equal to 1 over x1 times x1, x2, yeah? And as such, I get 1 over x2 over x1. And I can do that on everything in P1 except for that guy. All right? So essentially that allows me to build a coordinate chart. You could say, whatever you want to call it. I'll use psi. I haven't used that for anything else today. So like psi of, x is equal to x2 over x1 for, x an element of, let's say, u1. And u1 here is everything except for that.
This is a manifold.
And then I could throw everything out. I could just throw this out, right? And then if I do that, then a typical point in anything except for the horizontal ray, yeah, I could look at that like this, right? And if I take any point here, x1, x2, right? Then I have x2 not equal to 0, right? And so I can define the coordinate chart psi 2 of such an x in projective space to be equal to x1 over x2 for x and u2.
And now we've got an atlas.
And then all of projective 1 space is u1 union u2, and yes, that's an atlas.
There we go.
And you can prove that the transition functions that go from the intersection, on the intersection of these domains, right, which is like positive, the rays, I mean, since every one of these rays doubles both sides, right, it suffices to show that the overlap here and here is smooth because that covers everything. And so, in fact, yes, P1 is it's a one-dimensional manifold because we have coordinate charts which map to the reals. And on the overlap of their definition, you can prove that the transition functions are smooth. And if you can do this for P1, you can do it for Pn. We can do the same thing in Pn, where we just assume that we have the nth coordinates non-zero, right? You take all of the points in Pn such that a given, like the kth coordinate is non-zero, then you can use the equivalence to rescale that coordinate to 1, and just use the rest of the things to define the coordinate chart from Pn down to Rn. And as such, you can show that Pn is an n-dimensional manifold. This is by far the most abstract example of a manifold that I have in the manifold theory course, by the way. Because it's built, everything is built, it's very unnerving because the points in the projective spaces, the points in the projective space are themselves these sort of, they're lines. It's very, I mean, to me, it's very abstract, to my intuition. But anyway, yeah. So you have a one-dimensional manifold, apparently. Whatever that means, I haven't defined that in here, sorry. I am misbehaving more in this course than anyone. I mean, goodness gracious. I think this course is defining my maximal misbehavior, but
Maximum.
look, you should be able to kind of anticipate that this projective one space is homeomorphic to what? What do you think?
Probably real.
But can we cover the reals, we could the reals, like the identity function on the reals gives a global coordinate chart, right? So in a manifold theory, if we have a manifold, coordinate chart is a one-to-one mapping from the set to Rn.
Right.
And it has to be a bijection. And if there's two charts, they have to work together to give a smooth overlap function. But so for the reals, with respect to the usual topology, the Euclidean topology, I can just use the identity function for a global coordinate chart on the reals. I don't think I can get a global coordinate chart on this thing. So because of that, this is a lot like a circle. So to talk about projections, like for the circle, right? The kind of dumb thing to do, well, it's not too dumb, but if you take this part of the circle, you can just use the projection down to that as one coordinate chart for that half, right? And then you can take this piece and project that this way to this line segment, right? And that gives you another coordinate chart. And if I was smarter, you could have you could actually, well, let me not be an idiot. How do you, so you can also use the projection left or up, and you could do 4 of these half circle charts, and you can prove, but the formulas are very stupid, pi of xy is just equal to y or x, here. So the formulas are very simple, but you have to use 4 of them to cover the whole circle. The other thing to do is to be smarter about this, to talk about the manifold structure of a circle. Instead of doing that, just write the circle in the proper way. First of all, the circle, where is it?
Around the origin.
That's true. And the origin in what? The plane? Which kind of plane, though?
I don't know, I'm just a simple pole.
You're just a simple pole. in a complex plane. Let's see here, so e to the I theta, thank you for that. That is how I would write a point on the circle. And if I do that, then like the coordinate chart becomes stupid. Theta is the coordinate chart on the circle. But I can't make that a global coordinate chart because of the thing that we keep talking about in complex, the angle jump. See that it's not a continuous function on the totality of the circle, so I'd have to use like two different angle functions in order to cover the whole circle in a continuous fashion. So anyway, long story short, I'm pretty sure that this is homeomorphic to the circle. Projective one space is homeomorphic to the circle. In fact, we can argue that projective n space is homeomorphic to Sn. The one is manifold dimension here. Just like S1, this is S1. The one is the manifold dimension. All right, so maybe we'll get to that actually here. Okay, let me go on. Sorry, I'm misbehaving quite a bit today. Yeah, I hope so. Mm-hmm. Oh yeah, I think I did give. You know, it's the circle's a really easy thing to understand, but it is kind of a pain to cross all your I's and dot all your T's and everything with respect to the manifold structure, you know, if you're going to be picky. And making one part easier makes the other part harder, right? Like the projection maps where you're just taking x from xy.
From the inverse.
You know, yeah, then the inverse becomes very, like what's the inverse map of x? Well, it's x comma the square root of 1 minus x squared, you know? It's like, wait a minute, where did the square root of 1 minus x squared come from x? Well, you're trying to put it back on the circle. I don't know, it is what it is. All right, next example here. This is an example of examples, an Uber example. Let x be any topological space and A any subset of x. All right. 3.52. X be any topological space, A any subset of x, and here's the deal. So like here's a sort of boring picture of it. Here's x, right? Here's A. All right. And so we just define the equivalence. A1 is equivalent to A2 if A1 and A2 are in A. Otherwise, each point is just equivalent to itself. So basically, if you want to think about this, x mod the equivalence is what? It's essentially, you could look at it this way. Like I can write a specific formula for it. It's the set of like x such that, you know, x is an element of the complement of x by A, right? So it's stupid singleton sets like that, right? And what else? What's the other thing? So any two points in A are equivalent, right? So the equivalence class of any point in A is A. So that's this. So like geometrically, what this is doing